The transformative technologies shaping the next century of maritime engineering do not act in isolation. Sensors, artificial intelligence, digital twins, secure communication, high-performance computing, and autonomy are often discussed as separate innovations, but their true power emerges at their intersections. Sensors without intelligence produce data but no understanding. AI without physics lacks credibility and trust. Digital twins without real-time data become static representations. Secure communication without analytics adds infrastructure but little value. Autonomy without human-centered design introduces risk rather than safety. Transformation occurs only when these technologies converge into a single coherent system, where real-time sensing continuously updates physics-based digital twins, AI interprets system health and emerging risk, secure communication ensures trust and integrity, and high-performance computing enables continuous prediction and foresight. This convergence represents a fundamental shift from digitizing individual components to creating intelligent cyber-physical maritime systems. The next century of maritime engineering will not be defined by individual technologies, but by how effectively we integrate them into living, adaptive, and trustworthy systems. Traditionally, digital models in ship design have been static artifacts. They are created during the design stage, used for approval and certification, and then largely forgotten once the ship enters service. In this paradigm, the digital model's life ends where the ship's real life begins. In contrast, the digital twins of the next century must become living companions, evolving continuously throughout a ship's entire operational life. A living digital twin is continuously updated using real-time operational and environmental data. It evolves as the ship ages, as damage accumulates, and as operating conditions change. It reflects not only the ship as designed, but the ship as it actually exists and behaves. This is neither a purely data-driven model nor a purely physics-based one. It is a fusion of both. Physics-based models provide causality, interpretability, and safety margins. Data-driven methods provide adaptability, learning, and sensitivity to real operational behavior. Together, they enable reliable prediction of structural response, system performance, degradation, and remaining useful life. In this new paradigm, the digital twin is no longer just a design or verification tool. It becomes a persistent engineering partner, supporting operational decisions, anticipating emerging risks, guiding maintenance strategies, and enabling ships to be safely and confidently operated far beyond their original design assumptions. Artificial intelligence is already widely applied in maritime systems for pattern recognition, detecting anomalies, classifying signals, and optimizing operations. However, for safety-critical systems such as ships, this capability alone is insufficient. The next century requires a decisive shift from AI as a statistical tool to AI as engineering intelligence. Engineering intelligence means that AI must understand why something is happening, not merely that it is happening. This is where physics-informed AI becomes essential. By embedding physical laws, structural mechanics, thermodynamics, and system constraints into learning models, AI gains robustness, consistency, and engineering credibility. With this foundation, AI moves beyond simple detection. It enables diagnostics, prognostics, and decision support, identifying root causes, predicting damage evolution and remaining useful life, and recommending safe and effective actions under uncertainty. Crucially, explainability is non-negotiable. Engineers, operators, and regulators must be able to understand, validate, and justify AI-driven decisions. In maritime engineering, an AI system that cannot explain its reasoning is not intelligent, it is unsafe. In the next century, data transmission will become as fundamental to ships as steel, engines, and fuel. Real-time monitoring, living digital twins, and AI-driven decision-making all depend on reliable, continuous, and secure data flows between ship and shore. Satellite communication, particularly through global and low-latency networks, enables ships to transmit operational, structural, and environmental data in real time anywhere in the world. However, connectivity alone is not sufficient. Without data, integrity, provenance, and trust, digital information cannot be used confidently for safety-critical engineering decisions. This is where blockchain-secured data transmission becomes essential. By ensuring that data is tamper-proof, traceable, time-stamped, and verifiable, blockchain establishes a shared foundation of trust across all stakeholders: ship operators, designers, classification societies, regulators, and insurers. Secure data infrastructure fundamentally changes the role of data. It transforms data from a private operational asset into a trusted engineering resource capable of supporting certification, life cycle management, and regulatory decision-making. In the future, trust in maritime systems will be built not only on physical strength and redundancy, but also on the integrity, transparency, and reliability of the data that represents their health. Energy sovereign ships are vessels capable of producing, managing, and sustaining their own energy safely and reliably over their entire operational life, with minimal dependence on external fuel supply chains or port-based energy infrastructure. Energy sovereignty is therefore not only about low emissions, but about long-term autonomy, resilience, and life cycle integrity. Viewed through this lens, decarbonizing shipping at a century scale raises a deeper challenge than fuel substitution. Future ships must be designed as self-contained energy systems, able to support propulsion, onboard systems, and safety functions continuously over 50 to 100 years of operation. Technologies such as small modular reactors and advanced alternative fuels offer unprecedented energy density, endurance, and operational stability. At the same time, they fundamentally change the nature of ship design. Vessels powered by energy-dense systems are no longer short-life transport assets. They become long-life maritime infrastructure. This shift transforms the role of structural design and safety philosophy. Safety can no longer rely primarily on operational procedures or human intervention. It must be physically embedded in the ship itself through crash-worthy structures, robust shielding, system segregation, and fail-safe layouts that remain effective under extreme and accidental conditions. Energy sovereign ships therefore demand a new regulatory paradigm. Prescriptive rules alone are insufficient for systems expected to operate across decades of uncertainty. What is required is life-cycle, performance-based safety assurance, supported by continuous monitoring and verification. In the next century, energy will define not only how ships are powered, but how they are designed, operated, and governed. Autonomy in shipping is often misunderstood as the removal of humans from ships. In reality, the next century will be defined not by human absence, but by human repositioning. Autonomy exists across a spectrum, from decision support and conditional automation to fully autonomous operation. And at every level, the human role is transformed rather than eliminated. In advanced autonomous systems, humans act primarily as supervisors and guardians rather than continuous operators. They intervene in abnormal or unexpected situations, validate safety-critical decisions, and apply ethical and contextual judgment where algorithms alone are insufficient. This human-in-the-loop principle is essential for safety, accountability, and trust in maritime operations. At the same time, autonomy introduces new and subtle risks. Over-reliance on automation, erosion of situational awareness, skill degradation, and ambiguity in responsibility when failures occur. These risks cannot be mitigated by technology alone. For this reason, ethical, operational, and safety boundaries must be embedded into autonomous systems from the outset, not added as afterthoughts. The objective is not autonomous ships versus human-operated ships, but resilient socio-technical systems in which humans and machines work together, each performing the roles they are best suited for. In the next century of maritime engineering, autonomy will succeed only where human judgment remains an integral part of the system.
So why must future ships move beyond low carbon compliance toward true energy sovereignty?
Yes, energy sovereign ships are vessels, as I explained earlier, capable of producing, managing, and sustaining their own energy throughout operation with minimal dependence on external fuel supply chains or port-based energy infrastructure. Energy sovereignty extends beyond propulsion to encompass onboard power generation, storage, distribution, and intelligent energy management across the entire life cycle. Typical and representative examples of energy sovereign ships include nuclear-powered surface ships, nuclear-powered submarines, and fully electric autonomous ships. The concept of energy sovereign ships shifts the focus from mere low carbon compliance to operational autonomy, system resilience, and life cycle integrity. By reducing reliance on external energy logistics, energy sovereign ships enhance survivability in extreme environments, improve reliability during long-duration missions, and enable sustained operation under disrupted supply conditions. This paradigm is particularly critical for future safety critical and autonomous maritime systems, where continuity of energy supply underpins both operational effectiveness and system healthcare.